So in this case, we have a metal conductor in this U shape, and we have metal rod. The length of metal rod is L, and this length here is S, and we have a constant magnetic field going into a page. And so according to length law, we have magnetic field going in and area decreasing. So the current will cut against the decreasing, so it will be this direction, and the current will be not going wrong this way. So in this rod, current going up in the rod. Another way of using the right-hand rule will be velocity going that way, magnetic field going in, and so the current will be going up. And since we have current going up, magnetic field going in, so we have a force going this way. So in the first step, we're going to show the EMF is equal to L times V times B. This is chapter 30, and we're going to use Faraday's law. And then we're going to find the current. This is chapter 29. We're going to using Ohm's law. And then we're going to find the force of the magnetic field in terms of as a function of velocity. This will be chapter 29. And lastly, we're going to find the velocity function itself. This will be chapter 5 using Newton's law and as well as differential equation. Also in this question, we are not going to tackle the how back EMF affecting the current. So we are going to talk about how the current is changing due to the back EMF.
All right, so first step, we're going to try and prove that the EMF is equal to L times V times B, which we're going to start with Faraday's law, which tells us that the EMF, the magnitude of the EMF, is equal to the magnitude of the magnetic flux. We also know that the magnetic flux is equal to magnetic field times the area that it's going through. So we can put that in here, and we can simplify this a little bit. In this case, magnetic field is constant while the area is changing, and so we are going to pull, because it's constant, we can pull it out, and it will simply look like this. And the area in this case is L times S, so we can substitute that for A. Once again, L is constant and S is changing, so we can pull that out as a constant, like so. And then, as we know, the change in the derivative of displacement is velocity. So once again, we can simplify this some more. And ultimately, we're only worried about the magnitude, so we can finish it off with this equation.
And here in the second step, we got Ohm's law, which is from chapter 27. So here we got change of voltage equals to current times resistance. And so current equals to change of voltage divided by resistance, which from there we got the delta EMF divided by R equals to current. So from here we can find the force.
Okay, so we're going to continue using our chapter 29 material. So we already established the change in EMF is equal to the length of the rod times the velocity times the magnetic field. We also know that our current running through the metal is equal to our change in EMF over resistance. Using this, we can find that I is equal to L V B over R. And from there, we can substitute this in for our I, finding that force is equal to L L V B over R, cross with our magnetic field. We are only concerned with the magnitude of the force. So from there, we can drop the cross product because we know that they're perpendicular to each other. So we end up with L, length, velocity, magnetic field over the resistance, B. From here we can simplify further, condensing our L's and our B's. So we get L squared is equal to V b squared over r.
So now we know the magnetic field force equal to L squared B squared over R times B. And as we discussed in the intro, the force is going this way, so it's against the velocity. Okay, now I'm going to make this. We know the L is constant, B is constant, and R is constant. So I'm going to just define C equal to L squared B squared over R squared. This will make the following calculation easier because we're going to find the velocity as a function of time. Now, we have, in this case, we are assuming there's no friction, so the net force will be just the magnetic force, and F net equal ma. So we have ma here equal to, since force is going the other way, so it'll be negative c times the velocity. Okay, so I'm going to move n to the other side, so acceleration is just negative c over n times velocity. Okay, and we know acceleration by definition is the derivative of the velocity. So we have dv dt equal to negative c n velocity. So now we have a differential equation. I'm going to use the guess and check method to solve this differential equation here. I'm going to guess exponential function because exponential derivative is itself. So I'm going to take a guess that velocity is e to the negative cm times time. And so this is my guess here. So this is velocity as a function of time. And now I go to check. So take derivative. d of dt times of the velocity. This will, well, we just need the chain rule. So this derivative itself is exactly the same. And then take out doing the chain rule here. And yeah, so this is velocity. And with negative c of n, so this check out. So this is correct. So we know the velocity function as a function of time is negative c over m e negative c m over t. And we can actually sub this one here into this function, and then we'll get a force as a function of time. There was a small mistake on the final calculation that I forgot to add the initial condition, so I should add the initial velocity minus 1 because if t is 0, this will be 1. So yeah, so this before I should add the initial condition to the velocity equation.